Well, the first equation in the equation sheet is an equation which is representing say total heat that is needed in order to melt a certain volume of material, where a rho is representing the density of the material and capital V represents the volume of the material. There are three heat components when we want to melt a material, and those are included all in this equation. What are they? Let's move on to the next slide here to see what those components are. Indeed, this is the equation which I have written down here. The total heat is a sum of three heat components, and those include heat of solid plus heat of fusion plus heat of heating the liquid to bring it the temperature of it from melting temperature to pouring temperature. And if we take a look at this say diagram here, on the vertical axis we've got temperature against say time, and in this against time and also energy. As you can see, first we need to apply some energy which is used in order to heat the material when it is in the solid state from ambient temperature to the melting temperature, up to this point, melting temperature. And then some energy is needed in order to convert the state of the material from solid at this point to liquid at this point. So there is no change of temperature for some time. However, what changes is the state of the material from solid to liquid. And then as we add more energy, what happens is that the temperature of the material increases and it reaches to a certain temperature which is referred to pouring temperature, and that is well above the melting temperature. And for each one of these actually sections, there is a certain amount of heat energy that is involved, and these are referred to as three heat components, and those are all included in this equation right here. And then next equation is the equation which defines actually the velocity, velocity of the liquid material in the down sprue, in the mold system of the casting. Let me see what it is. I'm going to show it here. Here we've got the down sprue, as you can see. This is what is covered in the lecture material. We've got the cavity, we've got the runner, we've got the down sprue, which has got a conical shape, and we have got the riser. Indeed, this down sprue is playing an important role in the casting process, and the height of it is deciding how much pressure will be exerted on the liquid in order to fill in the cavity properly. So the velocity of the liquid at the bottom of this conical section right here is of importance. The same, and also the flow rate of the liquid at this point is of importance. So h is representing the height of this conical section, which is referred to as down sprue. So back to this equation, v, which is the velocity of the liquid at the bottom of the down sprue, is a function of its height, which is h. Of course, g is a constant value. Its value is given down here. Then we've got this equation 10.5, which is the equation for computation of volumetric flow rate. And as I mentioned before, it is making it possible for us to compute the flow rate in the down sprue and other sections of the mold system. It is a function of velocity times cross-sectional area of any section of the down sprue as well as the runner. If we have the velocity at a certain section and its cross-sectional area, we can easily compute the velocity of the liquid in another section if we know the cross-sectional area of that given section. And this equation is an equation which is very familiar to those who have done fluid mechanics unit, which is referred to as Bernoulli's equation. Next equation is the equation which is making it possible for us to compute the time needed for filling the mold, TMF, mold filling time. It is a function of volume of the liquid material divided by volumetric flow rate flow rate, which is computed up here. And then we have got another equation that is used for computation of the total solidification time, TTS, and that is a function of Cm, Mott constant. Mott constant is a constant value. Its value depends on the properties of the mott and the molten material. And also it is a function of volume of the material divided by A, which is surface area of the material. Exponent N is an exponent that is different for different types of, say, casting processes. However, for this lecture, we consider the value of 2 for the problems that we will be doing for, on computation of solidification time. This equation is very important equation in casting processes, and it is also referred to as Shorinov's rule. Okay, moving on. Now let's make use of these equation sheets in order to do the example problems. Example number 1 is asking us 1 cubic meter of a certain eutectic alloy. What is eutectic alloy? The alloy for a which has got the composition of eutectic is the one which has got the lowest melting point. When we have got two participating elements, a eutectic composition is the one which is giving us the lowest melting point for that given alloy. Is heated in a crucible from room temperature to 100 degrees C above its melting point for casting. Well, why 100 degrees above? Because we want to bring it to a pouring temperature, and that is normally above the melting temperature. Reason, if you melt it, just heat it up only to melting temperature, when the molten material is flowing inside of the runners, then it freezes and solidifies, so the cavity will not be filled in properly. So we've got to elevate it to a higher temperature so that when there is a drop of temperature, it is still in the liquid state. The alloy's density is 7.5 gram per cubic centimeter. Melting point is given 800 degrees C. Specific heat, CS, is given, and also in the liquid state, it is equal to 0.29. Heat of fusion, HF, is also given. So what we have got in this equation, indeed, include the amount of the material, which is V, 1 cubic meter, and then what else is given is, say, pouring temperature, which is 100 degrees above melting point. Melting point is given down here, which is 800 degrees C. We've got density or rho, which is given. We have got CS and also CL. All these values are given plus HF. So this is all we have. And what we need to compute is we need to compute the total heat that is needed in order to melt this much of material. On the basis of what is given, all we need to do is to make use of the first equation on the equation sheet. We are provided with everything. Rho is given. Rho is already given, and that is rho is given, and that is density, which is given up here, 7.5 gram per cubic centimeter, and then it's V, which is given. V, or say volume of the material, it is mentioned that it is 1 cubic meter. We've got to convert it to cubic centimeter. And when we convert it to cubic centimeter, it comes to this figure, 1 million. CS, CL, HF, TM, ambient temperature, which is 25 degrees C, pouring temperature, which is 100 degrees above melting temperature, and melting temperature, which is 800 degrees C. Everything is given. So we need to substitute all this in this equation, giving us this much of, say, this much of heat that is needed in order to melt the whole amount of material. So just simply we make use of the first equation, substitute the values, and do the problem. Moving on to the next problem. Example problem 2. A mold sprue or down sprue is the same actually section of the mold. It is referred to both as sprue and down sprue. Is 20 centimeter long. That is the height of the sprue, which is referred to, which is mentioned, and it is equal to, say, this much. This is H. The cross-sectional area in the base, A, is also given. Cross-sectional area in the base of the sprue is given. Where is the sprue? One more time. This is the sprue, so the height is given from here up to this point. This is H, and also cross-sectional area of this section is okay. The sprue fits a horizontal runner leading into a mold cavity whose volume is this much. Okay, back to the figure again. So the sprue is fitting a runner, and this is the runner. This section is runner. And what it was before in vertical section, this is sprue. From here to here, this is a sprue. And then from here to here, this is the runner section. And eventually, this is the cavity itself. This section is the cavity itself. And its volume is given. Determine the velocity of the molten metal at the base of the sprue. Velocity of the molten metal where? Right here. This is the area where we want to have the, say, okay. We want to compute the velocity right here at the bottom of the sprue. And then in B, volume rate of the flow at that same place, and also time to fill the mold. In order to get this computed, what we need to do is to take the second equation from the equation sheet, and this is giving us the velocity if we know the value of h. Value of h is already given, that is equal to 20, and g is the constant value. So what we need to do is to substitute the values and get this. In part B, the volume rate. Again, we take the next equation from the equation sheet, the equation for the flow rate, and then we have the value of velocity, which is just computed up here, and then cross-sectional area is also given in the statement of the problem, and that is given right here. So we substitute these values, and that will give us the volumetric flow rate of the molten metal in the mold. And then in part C, we've got to compute the time to fill the mold. Let's take a look at the equation sheet again. This one, the equation that is making us able to compute the filling time is this one. So we take it out from here, and then we get back to the problem, that one. Take the equation, volume of the material to be melted, and also Q. Q is just computed, and volume of the material is also given up here. So we substitute this value and also Q that is computed, and then it makes it possible for us to compute the time that is needed in order to fill the mold. So we are done. Next problem, problem 3. A cylindrical riser must be designed for a sand casting mold. This casting itself is a steel rectangular plate with dimensions as given. These are the dimensions of the rectangular casting. Previous observations have indicated that total solidification time, or TTS, for this casting is this much. So we have got the time for solidification of a plate with these dimensions. The cylinder for the riser will have a diameter to height ratio of this much, 1. Determine the dimensions of the riser so that its TTS, or total solidification time, is equal to 2 minutes. First, let's see what is the role of the riser. Let me go back to the previous figure right here to see what is the role of the riser. Indeed, the riser here is playing an important role. This is the riser. It's playing an important role. What is it? When solidification is in progress in the part itself, Then first the external surface freezes and solidifies, leaving some liquid material inside. And as solidification process is in progress, material shrinks. So some void spaces will be formed inside of the part. And we don't want to see that happen. In order to compensate for this, there is a riser right here which is providing us with the flow of the molten material. And this flow of the molten material, when solidification is in progress, does not allow formation of these void spaces or holes inside of the material. When the part itself solidifies, after this riser solidifies. So the solidification time, total solidification time for the riser is always greater than that of the cast metal. This is something that we need to take into consideration. Okay, back to the problem. Okay, what we need to do is to take the equation for total solidification time from the equation sheet, which is this one. What we have for the plate is TTS, that is given 1.6. And because we have got the dimensions of the plate right here, we can easily compute, say, V and also A. N is normally considered as 2 in the problems of this lecture, and the unknown parameter is now Cm. We compute the value of Cm on the basis of what we have at hand, and it comes to this much. The value of Cm will not change for the same mold, for the same liquid material. So if we want to design the riser, then the same amount of Cm will be applied. Now, the next part of the problem is to compute the dimensions of the riser for producing this plate in a way that the ratio of diameter to height is equal to 1. Okay. Why is riser cylindrical? The reason is that V to A ratio is a parameter which is defining the solidification time, is a very important ratio. As V to A ratio is greater, it means that solidification time is greater. And for riser, because we want the riser to last longer and solidify after the actual part, we've got to choose a VA ratio which is great. And it is a function of geometry of the, say, geometry of the part itself. Let's take a look at this figure here. If we are after designing a riser, we've got to choose a geometry which gives us the highest value of V to A. And if we take a look at these geometries, the one that is having highest volume to surface area ratio is sphere, this one. So we've got to make use of a sphere in order to produce the risers. However, a sphere is a geometry which is difficult to machine on the machine tools. Those who are familiar with machine tools and have got experience know that it is difficult to, say, machine spheres. However, it is much easier to produce cylinders, and it's still the VA ratio of this shape is greater than all of the other shapes in this slide. So if we cannot go for a sphere because of hardness in machining, we go for the next shape with highest V to A ratio, and that is cylinder, and this is a very easy to manufacture or machine geometric shape. Okay, back to the problem. Now, once we have computed, say, Cm for this, next we move on to computation of the dimensions of the riser, which is a cylindrical shape. We write the equation for volume of the cylinder, which is to be used for the riser, as well as an equation for computation of its surface area. Still, we do not know what the value of D and H is, because this is something that we want to compute. However, we know that the value of D is equal to H. This is mentioned in the statement of the problem. So we rewrite these two equations in a way that either H or D is eliminated. So we can rewrite the equation for volume when we know that D is equal to H in this form. Similarly, we write the equation for the surface area in this form. Now we have got only one of the two parameters of diameter and height in each of the equations. And for this given case, it is only diameter. Knowing that these are the equations defining the volume and and surface area of the cylinder, we can simplify the V to A ratio by substituting this value for V and this value for A. We can simplify the equation of VA, and it comes to D divided by 6. Still, we do not know what D is. Now, instead of VA in the equation for solidification, we substitute D divided by 6. And we know that for the riser, the total solidification time is given. That is given in the statement of problem, and that is 2 minutes. So having this at hand and having this at hand, there is one equation with only one unknown parameter, and that is D. So we can easily work out the value of D, and that is this much. And this value is the same value for height and also for the diameter. So the required riser in order to perform its function is 4.7 centimeter in height and also in diameter. And its solidification time, it's 2 minutes, which is more than 1.6 minutes, which is for the actual product. So it has got a longer or more, say, solidification time, so it can perform its function properly. Okay. Is there any questions on this? No questions? Okay, let's move on now to the homework problems which students are supposed to do at home. I'm going to explain one of the problems, and then you will do the rest of the problems at home, and of course solutions will be uploaded on the Blackboard so that you can look at the solutions if you face the problem in doing the problems. This is the same equation sheet that we have gone through it before. And then problem 1 is a problem similar to example problem 1. So I am leaving this to you in order to get this computed. Of course, solution is on the Blackboard. And then next problem, before moving to the next problem, let me just explain what is happening in this slide. Here we have got 4 different geometric shapes. One of them, the one at the bottom, is considered as the riser, and you know what the riser is doing now. And we've got 3 other geometric shapes. These are intended, say, products to be produced in a mold. So we are going to design a mold which is able to produce all of the 3 parts on the top with making use of this riser. How do we arrange them? How do we put them in the same mold system? Do we put them on a random basis, or we do it in a certain order? Of course, there is a certain order to be used for this purpose. How do we do that? We've got to arrange them on the basis of solidification time, or V to A ratio, as you can see it here. The one which has got lowest V to A ratio is the one which will be sitting further away from the riser. And then the next lowest, say, V to A ratio, and just keep going towards the riser itself, which will have the largest V to A ratio. Why is this? Because if a solidification is to happen in one of the parts, the one that will be solidified first should be the one that is further away from the riser. Reason is that if, say, for example, this part, which has got the smallest V to A ratio, is sitting in between, say, somewhere here, and it solidifies before the other 2, then it will block the supply of the molten material from the riser to the other 2 parts. So the one that solidifies first should be the one that is at the end. So this one solidifies, however, there is still a supply of the molten material to the other 2 shapes. Then this one solidifies, still there is a supply of the molten material to the other part, and eventually when this solidifies, we are done, and then the riser itself can solidify. So once the solidification process is completed, what we do is to cut the roller and also the riser and put it back in the furnace to be melted and reused. Okay, this is an indication of why we need to make use of Chorinov's rule, or total solidification time, or the simple form of it, that is only the VA ratio. Okay, now I'm going to skip this problem. Solution is already there. I told you, you've got to do it yourself. Now let's move on to problem number 2. In problem number 2, we are provided with this figure. This is another example of a mold system, and in this, what we have is actually a problem about casting, all the dimensions, everything is given. Let's read the statement of the problem. During pouring into a sand mold, the molten metal can be poured into the down sprue at a constant flow rate during the time it takes to fill the mold. So it will be poured from here, and then it just fills in all the cavity, riser, runners, everything. At the end of the pouring sprue, there is at the end of the pouring, the sprue is filled, and there is negligible metal in the pouring cup. Up here, there is negligible amount of the material left. The down sprue is 15 centimeter long. That is the height of this section. It's 15 from here up to here. H is equal to 15, which is given up here. So H given up here is equal to 15. And then its cross-sectional area at the top is 5 centimeters. Let me just get rid of the extra stuff which I have used. Okay. And then the cross-sectional area up here is given 5 square centimeters. And at the base, right here, at the base, 3.75. The cross-sectional area of the runner leading to the sprue is also 3.75. So the cross-sectional area of here is equal to that one. Again, 3.75. And the length of the runner is also given to be equal to 20. From here to here, it is 20 centimeters. What else is given? So we've got this figure as well, and cross-sectional area as well. The volume of the cavity is also given, this bit. The volume of it is also given. It is 1015 centimeter cubic. The volume of the riser located along the runner near the mold cavity is also given, 390. So we've got this one as well. Okay, this is also given. And then it takes a total of 3 seconds. It takes 3 seconds to fill the entire mold, including cavity, riser, runner, and sprue. This is more than the theoretical time required, indicating a loss of velocity. There is a loss of velocity due to friction. And then the task of us is to find theoretical velocity and flow rate at the base of the down sprue. Theoretical velocity and flow rate is easy. We have done it before, and we do it again. What do? We take the equations from the equation sheet. We've got the height of the down sprue, and we've got the cross-sectional area of the down sprue at the base. So we substitute the values of height. Of course, G is the constant value, and we can easily compute the theoretical value of velocity, which is this much. And the flow rate, once we have V at hand, cross-sectional area is given, so we can easily compute the theoretical flow rate. Next, in part B, it's asking us to compute the total volume of the mold, because all the dimensions are given. If I go back to the previous slide, the volume of the cavity is given, or the part is given, the volume of the riser is given, length and cross-sectional area of the runner is given, height and the cross-sectional area of the top and bottom of the sprue is also given, which has a conical shape. So it will not be difficult for us to put all these figures together and compute the total volume of the mold, which includes the volume of the cavity, the riser, the down sprue, and also the runner, which comes to this much. Please note that the down sprue has got a conical shape, so we've got to multiply this figure by 0.5, which takes into consideration the shape of the down sprue, which is conical. That's why we are multiplying by 0.5. Okay, in part C, it's asking us the actual velocity and flow rate of the base of the sprue. So the theoretical velocity and theoretical flow rate are already computed up here. This is theoretical velocity, theoretical flow rate. However, we are asked to compute the actual values of these two parameters. How do we do that? We've got to take into consideration the actual amount of the time that is needed to fill in the mold. And we take the equation for mold filling time out from the equation sheet. If we have the volume of the material, which is just computed, divided by Q, it gives us mold filling time. However, this time we have got TMF, which is 3 seconds, and we've got the volume of the material. We want to compute the actual value of flow rate, or Q. So we need to solve this equation for Q and substitute 3 for TMF. Then it gives us the actual value of flow rate, which is this much. And this is less than the theoretical value. The theoretical value was computed up here. This is the theoretical value of flow rate, or Q. This is the actual value. And as you can see, this is less. Now, by making use of the equation that we have up here, we can also compute the actual value of velocity. Now we have the actual value of Q divided by cross-sectional area, which is giving us the actual value of velocity. Again, as we can see, the actual value of velocity is less than the actual value, the theoretical value of the same parameter. Reason: friction, which was not taken into consideration in theory, but it exists. The friction of the molten material with the walls of the down sprue lowers the velocity and also lowers the flow rate. And that was not taken into consideration when we used the equation from the equation sheet. And then in the last part of the problem, which is part D, it's asking us to compute the loss of the height. What does it mean, the loss of the height? This one. The loss of the head. The loss of the head in the gating system due to friction. What is the loss of head? The head, we go back to the previous slide here. The loss of the head, if we take a look at this, there is a certain height of H that is needed in order to exert sufficient pressure behind the liquid molten material so that it can fill in the cavity properly. And now we have to compute the loss of head because of friction. What does it mean? It means that if there is no friction, a certain amount of head or height of the sprue is needed to apply sufficient pressure for filling the cavity properly. However, there is friction, and this friction should be compensated. And this compensation is making a difference. Now let's do the computation first, and then I explain how it works. Now we have come up to this point, and if we want to compute the head that is needed, we've got to make use of this equation again. This time, instead of say computing the value of a V on the basis of initial H, we do it the other way. We make use of the equation and we substitute the actual value of V that is computed right here in it and get the value of H out of the equation. And that's the way of doing it. We solve the equation for H and get the value of H that is needed in order to fill in this mold if there is no friction, and it comes to this much.